This is problem 45, and I'm going to show you my solution for problem 45, but we're going to kind of go through it fairly quickly. So for problem 45, we have a plastic sphere, but it's hollow. And they're only asking us to find the electric potential difference between A and B, but I'm going to show you how to find the electric potential difference everywhere. So we have this formula that we just used in the previous problem to find the change in potential. And they're asking us to find the electric potential difference. So here we can just go from B to A to find the difference. So our initial point is A, our final point is B. We just have to know what the electric field is in this region in order to be able to use the formula. So first we have to find the electric field, which if we're using this formula, it's probably because we can use Gauss's law to find the electric field. So we do Gauss's law, and this is what we have for Q enclosed. And because we're going from, where are we going? From A to B, we need to find the electric field everywhere in this region here. So we're looking for the electric field at R, where R is between A and B. So we've done this before in the electric field section. And we have the area, and we have Q enclosed. We use Gauss's law, and we get the electric field. Okay, so now we can put that into our formula here in order to find the change in potential between A and B. So we plug that in, we integrate, this is what we get, and we put in our limits of integration, and there we go. Okay, so I'm going to stop here for a moment, just if you want to pause the video and copy this down in case you want to go through it on your own afterwards. But what I really want to look at in this problem is not just how you would find the change in potential between A and B, but how you would find the potential everywhere. So here we go. For problem 45, we're going to find the potential everywhere. This handout that I'm showing you now is in the potential folder in my course folder for Physics 261. So if you want to look at it there, you can do so. So you don't have to copy it all down because you can find it in the potential folder. Okay, so if we're going to find the potential everywhere, our reference point where the potential is equal to 0 is at infinity. So we have to come in from infinity to whatever point we want. So we always start when v is equal to 0 if we want to find the potential at a point, because that's how we can get rid of the change in potential and make it just the potential at a certain point. Okay, so we have our formula there. We're going from the initial point to the final point, so it's final minus initial. Final is at R, initial is at infinity. From Gauss's law, we find that the electric field outside of the plastic, hollow plastic sphere, in this case where we're given the charge density, is this. Okay, so I'm not going to go through finding that, but that's what we have for the electric field. We plug it into this formula, and we integrate, and we go from infinity to R, and so this is what we get outside the sphere. Okay, now if you're inside the shell, and we've already kind of done this, but we just looked for the change in potential. So now if you want the potential, not the change in potential, but the potential inside the shell with the reference point at infinity, we're using this equation here. If you want to kind of write it down in one step, you would have to do something like this. Okay, so if I want to come in from infinity and go to a point R, which is inside the sphere, I've got my integral here. But the problem is when I go to plug in the electric field, it's different in the shaded region than it is outside outside. So if R is between A and B, remember an integral is just a sum, so I can sum up from infinity to B, and I'm just going to call that electric field 1. That's the electric field outside the shell. Whoops, I said B, didn't I? But I wrote R. So I can go from infinity to B with electric field 1, but then I have to stop at B, and then this is supposed to be a sum, but we got the negative sign out there, so let me just put it in parentheses. So then I can pick up at B and go from B to point R with electric field 2, which is the electric field inside the shell. Okay, so because we have a different electric field in the two different regions, we have to do the integral separately. So we start at infinity, and with electric field 1, we get all the way to point B, and then we pick up again with electric field 2 and go from there to our point, if that's in the shell. If it's not in the shell, we go from B to A, and then we have a new integral going from A to the point inside. So that's what we would have to do here. But if I want to find the electric field everywhere, I can just do it outside, and then when I do inside the shell, I can just take what I have here and say R is equal to B, and that's going to give me VB. Okay, so by Gauss's law, I have the electric field inside the shaded region. I put that in here, integrate, plug in my limits of integration, and now I'm going to take my VB, move it over to the other side, and then I can use my result up here to find VB and then plug it in. And now we have the electric field when R is between A and B. Okay, and then inside the hollow region, the electric field is equal to 0, which just means whatever electric field I have here when R is equal to A, the change in potential has to be equal to 0 because the electric field is equal to 0. So finally, I can say when R is less than A, the potential that I have here is just whatever this equation gives me when R is equal to little a. Okay, so if you want to go through that on your own, like I said, that handout is on the M drive in my course folder and then in the potential folder.